on this computer. Okay. Welcome. We're doing the FE exam review here. This covers probability and statistics. All the materials are available at statsclass.org. So you can go to statsclass.org and you can get the problem set, and also the solutions are there. So welcome back. We're going to start here on page, we're starting here, this is video 2, so we are going to start on page 4 with counting and probabilities. Okay, this first one I think I can just skip over once I understand, or once you understand the factorial. 6 factorial, what that means, so 6 factorial, what that means is just take 6 times 5 times 4 times 3 all the way down to 1. Okay, so that's what 6 factorial represents. Once we know that, I'm good to go. I can just write that out. There is, at least I think there is on the TI 36, okay, a factorial or combinatorial. This is actually what this is labeled would be 6 choose 3 is how this would be identified with probability statements. Okay, 6 choose 3 is what you're looking for there. The only other thing I should tell you is that 0 factorial is actually 1. Okay, we define 0 factorial to be 1. So if I do the simple math here, I got 6 times 5 is 30 times 4, right? And then what's 6 times 5 times 4, 30, 120 is it? And then I'm down to 3 times 2 times 1, but 3 to 1 is the same as 3 factorial. So essentially what I need here is 6 times 5 times 4, which is 130, or 120, excuse me. All right, that's that one. Number 12. Cards and dice and other things. I'm 100% honest with you. I don't know if they are going to have these types of questions on the FE exam. They are in the sample set of problems. So the sample sets that I've grabbed and looked at, you do have problems like this. I never really understood why we need to do probabilities with dice and cards and why we rely on them so much, but whatever. I'm not making your exam, I guess. So let's talk through what we have here. Given we have 52 decks of cards, the other thing that I need to know or understand here is we're doing these without replacement, which is going to be important because if we're drawing 2 cards, on the second draw, I only have 51 cards available. So without replacement or with replacement comes into play here. Okay. Given that an ace was drawn on the first, so here, if I'm trying to work through this, notes that I would be taking if I was trying to solve this one, the first draw, okay, was that an ace was drawn. They're telling us that. Okay. And then on the second draw, they want to know that it's also an ace. Okay. So oftentimes what we do when we're doing things like this is we would label this as event A, let's say, and this as event B. Okay, so if you're looking at the formula sheet, for example, for stats and probability, they're going to do things like, what is the probability of B given A? So that's how we write that. What's the probability that I get an ace on the second draw? Okay, so that's event B here. Ace on the second draw. The vertical line is given that an ace was drawn on the first draw. That's event A. Now, the formula for this is going to be A and B divided by the probability of A. Okay, so that's what that, if you go back, I mean, they give you that formula sheet on your FE exam. They give you that formula on the FE exam. Don't try to memorize it. Just go off and look it up, and if they have a conditional probability, okay, probability A and B divided by probability of A. All right, so now probability of A, what is probability of A? Where am I at here? Probability of A is getting an ace was drawn on the first event. Okay. So ace was drawn on the first event is probability of A. There's 4 aces in a deck of cards. Okay. And I'm talking the first draw here. There's 4 aces in a deck of cards. So there's 4 out of the 52 on the first draw. So probability of A is just simply 4 divided by 52. That's going to be my denominator. My denominator is 4 divided by 52. Now I need to know what the probability of A and B is. Okay, the probability that I get an ace on the first draw and I get an ace on the second draw. Okay, well, the probability that I get an ace on the first draw is the 4 out of 52 again. Okay, and getting an ace on the second draw, we're going to multiply these two probabilities together. And I'm going to have 3 aces left. And there's only 51 cards left in my deck. So 4 times divided by 52 times 3 divided by 51. So these and probabilities, they get multiplied together. Okay, there'll be an example later of an or probability. If it has probability A or B, those are a little bit more complicated. But and probabilities you get to multiply together, assuming events are independent of one another. So whatever 4 divided by 52 times 3 divided by 51, all that crap divided by 4 divided by 52, whatever that is what my answer is going to be there. I'll let you, 1/17 maybe is what I have highlighted here in my notes, but. So again, I don't have the formula sheet here in front of me for the exam, but the FE formula sheet for probability and statistics for the FE exam definitely has those conditional probabilities. That's called a conditional probability. It's a given probability, as a given. Anytime you have given, you're looking for that. Okay, next one's a little bit more straightforward. The English alphabet contains 26 letters. How many 3-letter codes can be formed if there's no repetitions are allowed? Okay, this is going to be simply 26. If you think, at least how I would draw these out, that's my first letter, that's my second letter, that's my third letter. Okay, how many choices do you have for the first letter? 26. Okay, no repetitions. How many choices you got for the second letter? 25. No repetitions. How many you got for the third letter? 24. Whatever 26 times 25 times 24 is. Okay, how many combinations, or what is it saying? How many 3-letter codes can be formed? Okay, well, you have 26, no repetitions. What if there was repetitions allowed? Then what would the math be? Yep, 26 times 26 times 26. Yep. If you do allow repetitions, then I get 26 choices on each one of them. Okay. 14. It looks like I deleted one of the problems maybe. How many combinations of license plates would be 3 letters followed by 3 digits? I have that in the solutions, but it looks like I dumped it here on the. So you have one extra problem in the solutions, it looks like. Whatever, that's fine. Let's do another conditional one again. Okay. How many times out of 100 attempts are you likely to select a red ball and then a black ball in the second from a bucket containing 40 balls? 25 black, 35 white. Okay, the first ball is to be reinserted into the bucket. So we're doing these with replacement here. Okay, so they want, what is my two events here? Event A is going to be red ball drawn. Okay, red ball drawn first, I guess I should be careful. Event B is going to be black ball drawn second. And what do they want to know? What are they asking here? How many times? Well, that's just telling you to get a probability. The red ball first. Yep. What is the probability of A and B? So they want to know the probability of A and B. Okay. So when the events are independent of one another, which they are in this case, I get to just multiply these two probabilities together. So I guess this one isn't that interesting. Sorry about that. This is just going to be another one of multiply the two events together. So probability of A is, what is it? Red ball drawn on the first. That's going to be 40 out of 100 there. And then because they're doing it with replacement, black ball on the second is just going to be the 25 out of 100. Because they put the ball back to 100 on the second time through. So 0.4 times 0.25, which is 0.1. And then they're asking you to express that in terms of how many times out of 100. So obviously 100 times 0.1 is 10 times. The answer there is C. Answer for that one is C. So I thought that was going to be a little bit more interesting than just multiplying. So when the events are independent like that, you get to multiply those two together. Those two, the two events, you multiply those together. Okay, let's do a little bit more probability. We're going to do some ORs now. And luckily for us, they're doing this with a table, which makes my life a little bit easier. And understanding how an OR probability works. Okay, so again, from my formula sheet for an OR probability, okay, probability A or B, what I do there is I sum up the individual probabilities. Okay, that kind of makes sense. With an and I multiply, and with an or I add. But as you'll see, you can get into double counting, okay, if the events are not mutually exclusive. Another probability word that gets thrown around sometimes. So if events are mutually exclusive, that means they cannot occur together, then the probability of A and B is equal to 0. So this formula becomes easier if the events are mutually exclusive. And I'll have to tell you that in the problem. We'll see in the context of this example that they're definitely not mutually exclusive. Okay, so what are my two events here? They want in group A or RH negative. Okay, group A. So what I need to do for group A is look at both the RH negative and RH positive. There's 40 people there. And how many of those are RH negative? 5 out of 40. So if I want to write, if I'm going to say, let's just be a little bit careful here in writing these out. Event A is, let's just say group A. They belong in group A. And then event B is that they're in RH negative. So what is the probability of A? What is the probability that they're in group A? My bad. Okay, I got to be careful here. Probability of group A. I had how many total in group A? 40. Okay. Out of how many altogether? 40 out of 100. I was getting ahead of myself there a moment ago. So 40 out of 100. That's going to be probability of A. There's 40 in group A out of 100. Now, if I do probability of B, probability of event B is going to be RH negative. How many total RH negatives did I have? 14 out of 100 again. Okay, so here I'm going group A and then RH negative as well. Now, when I do that, I took group A, 40 out of 100. I did RH negative. How many times did this 5 cell get counted? Twice. It got counted when I was going this way. 5's getting counted when I go that way. And 5 is getting counted when I go this way. I double counted those 5. So what am I taking out? The 5 out of 100. I got to subtract that back out of that. So the probability of A and B is that 5 out of 100. So 40 plus 14 is 54 minus 5 is 49. 49 out of 100.49. So or probabilities here, you're going to have to worry about subtracting out that double counting. Unless they're mutually exclusive. They're mutually exclusive. Mutually exclusive mean they both cannot occur at the same time. And then that probability A and B would be equal to 0. Compute the probability that a randomly selected person does not have group B and is not Rh positive. Okay, does not have group B and is not Rh positive. Probably could do this with just crossing things off in a table. Let's see if we can do it that way. If they are not Rh positive, then that means that these are all out, right? Oops. Sorry. If they're not Rh positive, that means this row is gone. I mean, these outcomes are gone. Maybe I shouldn't delete the entire row, but these outcomes are gone. And if they're not in group B, then that one's gone. So what do I have there? 6, 12, 11 plus 1's 12. 12 out of 100 left. That's going to be easier. If they give you a table like that, just take your pencil and start crossing crap out. I mean, there's some formula for that, but I would just intuitively do that one. Compute the probability that a person is group O, given that they are Rh positive. Okay, so now let's back out of that a little bit. We know, given that they are Rh positive. So that means this stuff is out. We know that they're Rh positive. Group O is 39, but what is my denominator? Not 100, because we are given that they're Rh positive. My denominator is 86. So whatever 39 divided by 86 is. So again, if they give you one of these tables like this, and they're asking you probability statements off of them, ands are really easy because that's where they intersect. Ors, you just can walk through that like we did with this example here. Just remember that they're double counting, because one of the options is going to be where you don't subtract off the probability of A and B. Right? One of your multiple choice items is going to be, oh, you forgot this extra step in the equation. So don't forget that step. All right. We okay with probabilities? Enough of those. Cool beans. Let me do 2 more and then we'll move on to regression. These examples here, I'm going to go ahead and just go to the solutions for these next couple, because the way to tackle these are with what we call probability trees. So I'm on 18, it looks like. Problem 18 is what I want to do. Again, I'm looking at the solutions here. So here's the setup. This is going to be a classic example of I want to try to sketch things out, understand what's going on through the use of what we call a probability tree. So an individual has 3 different email accounts. Most of their messages, 70%, come from account number 1, 20% from account number 2, 10% from account number 3. Okay, so right off the bat, if I'm trying to think about this in terms of a tree, okay, is literally just making 3 branches. The one to the left, obviously, is account 1. The one in the middle is account 2. The one on the right is account 3. Now, On account 1, only 1% are spam. Okay. So now when I'm building my probability tree, when I'm down this branch, 1% are spam. That means 99% are not. On the second account, it's 2% spam. And on the third account, it's 5% spam. Now, what are they asking for? What is the chance? Okay. So what is the probability that a randomly chosen email is going to be spam across these 3 accounts? So how I tackle that is I'm going to multiply these probabilities together. So over here on the right on my tree, all I care about are the spam arms there. So to get down to the first spam on account number 1, I know that 70% of my emails come through account number 1 and 1% of those are spam. So I'm going to multiply those together. Whatever 0.7 times 0.01 is, add some zeros there before that 7. The second one, I'm going to multiply the 0.2 times the 0.02. And then for the third, obviously, I'm using the 0.1 times the 0.05. So this is a total probability because I'm trying to figure out the chance of spam, not just on one account, but across 3. Okay, so that's a total probability idea there. And again, the way to attack this, at least how I would attack that, is through the use of these trees, because then I can clearly see how things are going to come together for me. Obviously, if you get a probability value over 1, you've done something wrong. You get a probability value under 0, you've done something wrong. Okay, so if you start adding things together here, you're going to really quickly, I mean, if you take the 0.7 and add it to 0.01 and 0.2 and add it, you're going to end up with a probability greater than 1. So you know you've made a mistake there somewhere along the way. Okay, I'm going to skip number 19. That's just another one off of this same probability tree. Number 19 does use something called the Bayes rule. Okay, which I will let you look at that example there and just walk through what the Bayes rule is about. Okay. I think the next one is regression. So let's take a pause here. Again, I'm going to cut the video down. Be back here a little bit with linear regression.